don't forget. I'll change it to speaker view so I don't forget. Okay, and it'll get me up there. Right here. This thing's still buffering. So just so you know, we are going to start up probably at page 195 in the workbook. 195. Okay, there's got the video paused. All right, LC oscillators. Let's make sure I'm on the right camera. Get the right zoom screen here. 2 minutes so I can see a little bit. Oh, and there's something in the chat. Let me see what's in the chat here. Oh, got you. Okay, got it. All right. Now, we're basically going to do a topic here. We're going to talk about LC oscillators, okay? And just so I have something up here to show you, I'm going to draw a simple version of this, and we're going to talk a lot about this. You're going to see me write this with a double throw switch. I don't know if you recall what a double throw is. That was the kind of switch where you could go to 2 positions, an A-B switch if you want. And so we're going to talk a lot about this, and we're going to do a couple of passes through this. So I guess what I'm saying here is we're going to do a very serious worked example and kind of go through the gritty details in a minute. And I looked at the solution. The solutions are going to have a lot of these little details that I'm going to talk about. So before we get into that, I want to talk about this conceptually. And there's some key phrases that I want to talk about that are going to be critical for the rest of the semester. And so you may want to take notes, you may not want to take notes. I feel like this may be one of those topics where if we pay attention and group together, you may not need the notes, but this is, you may actually want your notes here. So if I'm going too fast while you're taking notes, say something, all right? So I want to make sure you get this concept down. Now, the idea here is the following. Let's walk through what we suspect would happen. Let's say I put this in position A and leave it there. What's going to happen to the capacitor if you put this in position A and leave it there for a long time? It's going to charge up, right? Eventually, how much current is going to be flowing? None. All right. So we expect that after a long time, right, this capacitor would have its positive plate this way, negative plate this way. Do you agree with that polarity? Polarity, we can't avoid polarity anymore. We have to actually make sure we understand it now. Right? This plus plate is going to attract electrons off of here, magical fairies of chemistry, bringing them down this way and put them over there, right? So now label A and B here. All right. So now I want to switch it to B. What's going to be true about the battery and this resistor? In particular, do they matter or do they not matter anymore? They shouldn't matter. We've taken them out of the circuit. Do you agree? There's not a completed loop here, right? And I guess I should be careful. Let me label these. Let's say this battery was E. Let's say this resistor was R. This capacitor was C. This inductor is L. Okay? So if this voltage right here is E, what should be the voltage across the capacitor? E. Does that make sense? I bring that up for what reason? What does a capacitor preserve when you change the switch? Charge, okay, or voltage. Charge and voltage are the same. Let me ask you this. What's the initial charge on here? It's EC. Right? So we know the charge. I know the change. Just for the sake of space, I'm going to write this VC. Right? And maybe if I go this way, I'm going to see if I can get a little closer here. Is that a little better on Zoom?
Yeah, looks good.
All right. So we got the voltage here and this here. When I change the switch, that stays the same. Agreed? Well, what does an inductor preserve? Current. We talked about this last time. Well, what's the current in the inductor right now? In this page, it would be 0. So what does it have to be when we change the switch? Okay. Now, I want to point this out. This is still a plus terminal. This is still a minus terminal of the capacitor. The capacitor is now the energy source for the circuit. Agreed? Well, we could do KVL, couldn't we? What has to be true about the voltage on the inductor? It has to be what? Yes. Is this a contradiction? Do you agree would have to have this polarity like this?
Yeah.
It's going to oppose it, right? So this one is trying to act like a voltage source driving current this way. This says, I oppose you. Is this a contradiction? What was the equation for the voltage on an inductor? Do you remember? Voltage on an inductor was minus di dt. So the idea here is the current is 0, but if I know this voltage is E, right, minus E over L would equal di dt. The idea is just because the current is 0 doesn't mean it's going to stay 0. It's going to change at this rate. So, right, think about it. If you're plotting current versus time, initially the slope, oh, well, we've got a minus sign here. I'm going to throw in an absolute value now because I don't want to talk about it. The size of the current would start out with some slope, E over L, and then it might do something else. Is everybody okay with that? All right. So you can see this minus sign is reflected in how this is flipped compared to that. So I hope that makes sense. So when you see me, a lot of times what I'm going to do is take the absolute value of this equation and think about the polarity in my pictures. So I apologize if you don't like that style. While we've got that up there, I'm going to bring this up. Q was equal to voltage across the capacitor times C. How does this relate to current? Do you remember? How do we get from Q to current? We're going to use that all day today. You remember the definition of current in terms of charge? dq dt, right? So I'm going to write this down that way. Do you agree that I should equal C times dV dt? Do you remember we wrote this last time? So the idea is, if I'm trying to understand voltages, inductors, and current, this is an equation that relates them. Similarly, voltages, capacitors, and current, this is the equation that relates them. And right? The idea was whatever's inside the derivative is what's preserved. You call that? You can cut. I use that equation to help me remember that. All right, great. What's going to happen next? If we're running this thing for a while, do you agree the charge is eventually going to start leaving here and there's eventually going to be current flow? Okay. Do you agree at some point this is going to be almost uncharged? And do you agree that there's going to probably be a lot of current flow as it's trying to, right? Initially, there's no current flow, and then when it gets close to discharging, it's going to be pushing current really quickly. I make that claim. So I'll just say after a while I'm not even going to draw the resistor anymore because it's just taking up space and I have limited board space. The idea is this voltage is going to be approximately equal to 0, but there's going to be some current flowing, right? That's the charge. In this case, there's going to be current is not 0. All right. Well, let's do KVL. This voltage is 0. What does that tell us about this voltage? Yeah. What about the charge on this thing? Now here's my claim. See if you buy into this. An inductor you can think of as a solenoid, right? Just a coil of wire. Here's an inductor. So a coil of wire on some Quaker Oats, all right? We'll discuss this later. Here's another set of inductors, just some wire on a pipe, right? Just that, right? So it's just, an inductor is basically a coil of wire. What do we know about these inductors? What do they oppose? Changes to what? Current. They preserve the current. So here, if you believe me, see if you follow. This is the crux of the argument. When the capacitor gets close to discharging, current's already flowing because the charge has to be leaving. Well, the inductor wants to keep that current going. So eventually, even though there's no voltage, there's energy in the magnetic field that keeps the current flow. So what's going to happen if you keep the current flowing? After a while. Well, just remind me, if current's flowing this way, which way are electrons moving? Well, if this current persists, what's going to happen to the capacitor? It's going to flip the polarity. Do you agree? So after a while, it's going to look like this. Eventually, the capacitor is going to charge up the opposite way. And then this one is going to have no current because the capacitor will eventually stop the current. Do you see we're basically back to this? Yeah. So let me see if I can give you a physical example of this. And I don't know why. Here's an example. Make sure I can do this. Now think about this. I don't know if this is showing up on Zoom here. This pendulum is supposed to be simulating what we're talking about here. I want you to think about it this way. We start off with all potential energy. Now it goes to all current kinetic energy. Then it comes back to all potential, right? It's the pendulum swinging back and forth. Up here, it's all potential energy, MGH. Down here, it's all 1/2 mv squared at the bottom, but MGH is 0. And then it goes up, right? Is that making some kind of sense that we see this as an oscillator? This is why it's called an oscillator circuit. The energy is going back and forth between different forms. Is that cool? That's the concept we're trying to understand. And then, do you agree after this, the whole cycle would repeat in reverse? Yeah. Let me ask you this, important fact. How much of a cycle have I shown? Like, forget about this part. This was just putting some energy there to get it going. When I switch it, this is when the oscillation started, right? How much of a cycle have I shown? Half a cycle. It's important to note that that's like saying, right? Whoops, let me do it like this. This one is potential energy up on the right, or whatever side it is on Zoom. And then as it swings down here, all kinetic, then we're going over to here, right? This would be all potential energy on the other side. The polarity is flipped, right? So the full cycle is you have to go all the way over, then all the way back. So keep that in mind. Notice, we expect this thing to oscillate. we expect it to take half a cycle to get from initial polarity to flipped polarity. So how much time do you think it takes to get from this stage to this stage?
What's that?
This is a half of the full cycle. So this would be a quarter cycle. So every quarter cycle, we get this flip-flop between the capacitor and the inductor energy. So far, so good? All right. Questions on Zoom? All right. Now let's go over here. So I don't normally do this much theory in advance. Normally I go right to problems, but I'm going to do this one. Generally speaking, if we try to understand this circuit and get a mathematical equation for it, right? This concept doesn't help us that much yet, right? So we need to understand an equation as well. What is the trick that I've used over and over and over this semester to go from a conceptual picture like this to getting an equation that we can use that has time in it? Do you know? What's that? Well, usually it's right before plotting is the end result of that. You're right. So we want to get a plot of this because otherwise we can't really understand it. I agree. What's that? You know what? I'm just going to tell you because I'm not sure if my question is any good. So usually what I try to do is I try to take KVL at an arbitrary time. And that might not have been what you were thinking about. So what I mean is, let's draw a capacitor here. Let's draw an inductor here. We don't need the battery and stuff, but I want to do this at an arbitrary time. Some time that it could be at max, it could be at min, it could be anywhere in between. And then it forces me to write this thing down in terms of only the symbols. So do you agree? I'm going to cheat and say voltage across. You've noticed I've stopped writing the deltas. I apologize. I'm lazy. I'm a bad person. But I hope you agree that voltage across the capacitor plus voltage across the inductor should add up to 0. Now, I want you to give me a little bit of latitude. I'm going to hand wave the minus signs, but I promise to come back to it later. You might be saying, wait, shouldn't it be plus, minus? Do I need to work? I don't care. But now, how does this voltage across the capacitor relate to charge? What's the home shopping network?
Oh, VC.
So you said Q equals VC. So wait, solve for VC.
Oh, Q over C.
So this is Q over C. That's all I wanted to point out. Are you okay with that? Now I'm going to gloss over this, the polarity issue. You know that in the definition there was a minus sign here, but we're exiting on a different. I don't want to. Right, so we know that there might be, depending which way you're going around the loop, right? We might have to deal with plus minus signs. I just don't want to talk about that right now. I want to get to the result. So you may be really confused on the minus sign here. Just shh, I don't want to explain. We can talk about it later. In this case, this is almost a differential equation we can understand. But remind me, how does I relate to Q? It was, yeah, the derivative, right? So watch this. Do you agree that is still true? All I did was I wrote I as dq dt, so now I get a sec. Oh, wait, shouldn't that be a second derivative downstairs to you? I can do a second derivative of it. Cool with that? And now I'm going to rearrange this to solve this for d squared q dt, right? So I'm going to say d squared q dt squared is equal to minus 1 over LC times Q. My claim is that this result works. And you might be saying, wait, the current through the inductor, there's a minus sign that has to do with the charges leaving the capacitor relating to this other minus sign. And so you might be saying, worried about that. We're not going to worry about that till later. But for right now, this is my claim. The charge on the capacitor relates to its own second derivative with a minus sign. So, gosh, but what I really want to understand is, my goal here is what is Q of T? So at first this may seem crazy, but my claim is I need a function that returns itself with a minus sign after two derivatives. That is the claim, right? The only way this could work out is if when you plug in your equation for Q and take two derivatives, you get a minus sign and a constant sitting out front. Do you know any equations that give you a minus sign when you take two derivatives? What's that? Sine and cosine. So Q of T could equal, that sounds like an oscillator, doesn't it? So that's why I was kind of like, whatever, mine. But one possibility is these are some possibilities, right? Now, which one of these do you think applies to our particular situation? In particular, think about these two functions. And think about, what were you thinking?
Matters about polarity.
Okay, let's talk about it. Yes. So do you agree you could get a plus minus? Oh, hold on, let me get back here. Jesse brought up a huge important point that I was hoping to gloss over till later. The polarity matters. We could have a plus or minus here, right? Absolutely. In this case, this is when the time starts for us. Does this look like a cosine function or a sine function, and why? Cosine, why? It's not zero, right? So that's how we know for this particular case, this one probably works. And then Jesse brought up the other point. Should I use plus or minus in this case, if you had to choose? So I would choose plus as well, because I don't have to think as much, right? So for us, it just depends on which way you measure the charge. Are you measuring it upside down or not? It doesn't really matter. So that's my claim. Well, now I want to be a little bit careful. I want to put a subscript O here. Right? So just because I know what's coming in the next chapter. Right? Now, let's plug this in and see what we get. When you plug this in, right? Let's take ddt of Q max cosine omega naught t. So to be clear, this is an omega, not a W. It's an omega. For my classes, if you see me write this, that's a W. This is an omega. That's a capital W. Just so you know, W is not the same thing as omega. W means weight, mg. All right. What do we get when we take the derivative of this? Negative, because you get a derivative cosine is negative sign, so I get a negative. What happens when you have a constant inside? Pops out, so it's going to be negative omega naught Q max sine omega naught T. Didn't see that till now. Okay, that's cool. That does not help me oscillate. Okay. All right, whatever. Is that okay? Can you see it on Zoom?
Yep.
All right. Now let's take the second derivative. What's that going to be? When I take the derivative, do I get another minus sign or not? No. Do I get another omega naught? So it's going to be minus omega naught squared Q max sine, wait, cosine, I screwed up. That was the whole point. Watch this. Do you agree this right here, we just found the second derivative of Q, right? Isn't that what we just said? So now I'm going to look at this boxed formula here. My claim is minus omega naught squared. I'll get out of the way. That is that. Sorry about that. That's the claim. Well, let's start picking this apart. Are these things really equal? They don't look exactly equal to me. Do you agree no matter what time you plug in, the cosine is going to equal the cosine? So that can cancel. You agree Q max is Q max? Huh, what about the minus signs? Cancel. So what, if we want this to be true, what does this tell us? That is a huge deal. We know omega naught. Well, we need to know some terminology here. And so I'm going to talk about this in a minute. Mathematically, we see a bunch of symbols. What does omega naught mean? What does omega mean in physics? Angular velocity. Now, in this case, we don't want to use velocity anymore, so we're going to change it to angular frequency. All right, so it's the same thing, though. So this is angular frequency now. Same thing, no. Angular velocity, angular frequency. All right. And now we should be careful here. What is Q max? That's the charge amplitude. Right? It is not the charge as a function of time. It's the charge amplitude. It's the maximum amount of charge in the oscillation. And so Q as a function of time is charge. Notice the main difference here. This is something I really need to stress. There's a difference between charge amplitude and charge. We are going to use this for weeks. You've got to be perfect on that, okay? So the charge is Q max. Actually, let's highlight it in blue here. So use red. Okay, so these are kind of the big summary results out of this that matter. Is that all showing up on Zoom there?
Yep, all good.
Okay. All right. So we have figured out, we knew this thing was going to oscillate. Now we know the frequency at which it oscillates. The amplitude is going to be called Q max. We just chose that name. We could have chosen a different one. And in this case, we see that this could be a cosine wave. It could be a sine wave. We saw, I guess maybe you noticed that this. Are there any other solutions that you could think of, or is that it? I could think of infinitely many more. It could be any combination of these added together as well, right? It could be some sine and some cosine, right? Basically, in general, you could choose a different starting point in the cosine wave, and there's infinitely many ways to start, right? So you could be all cosine, or you could be all sine, or somewhere in between. That's what I'm saying. So I'll address that in just a minute. And I think we are now ready to talk about page 195, unless you guys have some questions. Good? All right, so I'm going to erase this board and I'm going to write up the summary bullets now and see if this makes sense. And then we're going to do worked problem and then we'll, yeah. So. And you may want to summarize this in your own way. I'm probably going to add some stuff that's not in there. All right. So our summary, we did use Q equals voltage on the capacitor times C. And we usually said that the current is something like C dV/dt. That was our first piece. We used that somewhere. Also, we know that the current, we also know that the voltage across the inductor is minus L di dt. All right. This is something that maybe we should remind ourselves. What was the equation for the energy stored in a capacitor? Okay, one half
QV.
Yep. But there's probably a nicer way to write this one. This could be rewritten in a couple of different ways. What was the most common one that we've used a lot?
1/2 V squared C.
Okay, 1/2 V squared C. What was the other way?
Q squared, 2C.
Q squared. Now, my question to you is this valid for functions of time, or is this only valid for the max, or both? What does your gut tell you? Both. If you plug in Q as a function of time, you get U as a function of time. If you plug in Q max, you get U max. All right? So I would like to use this one, and so, but any of these others should work, right? So, all right, that's fine. Let's see if you remember this one. Does anybody know the equation for magnetic energy?
Li squared.
Yes. And again, if you plug in the maximum current, you would get the maximum magnetic energy. If you plug in current as a function of time, you would get energy as a function of time. So far, so good? I've already used these words. I better write them down. I like to call this electric field energy, because the energy is stored in the electric field in the capacitor. Capacitor is creating an electric field. You know what I'm saying? So, and this one, current creates a magnetic field. Inductors oppose changes to that magnetic field, and that's where they get their inductance from. So I argue this is great to call this mag field energy. So far, so good? That's going to be useful to us when we're trying to write these down. For the problems that we are going to solve in this chapter, we can simplify it to these two options. Either the capacitor is going to start with energy or the inductor is going to start with energy. And we talked about maybe you need to worry about the polarity. We'll call that the Jesse effect. All right. Usually you can clarify that with a picture or something in on a test question. If you're worried about that, you just be like, look, I think it's this way. This is the equation I'm going to use. I'm like, okay, whatever. Just make sure it works out in the end. All right. So here, the plus minus depends on initial polarity. Does that make sense for the sine and cosine bit? And if you want, all this stuff is in here on page 195, I hope, right? Now, check this out. We only solved for Q, but remind me, how do we get current as a function of time? How does it depend on charge? The derivative of it. You see what I'm saying? Yeah. So do you agree? We're probably going to get something that looks like, what happens when I take the derivative of this first one? Okay, so maybe minus or plus, depending how you want to think about it. Do you agree an omega naught pops out? Sine? And then, to be honest, I don't really care here about the sign, but now I'm stuck with it. Right, because see how this one's not going to give you, right, it's derivative sign. So I'm just going to make them both plus or minus, just so I don't have one looking weird. Okay, that is a technical move you can do, actually, if you didn't know that. The flipped plus minus. It works in certain special cases for certain problems like this one, but I don't want to talk about it right now. Huh. Is there a fun name I could call this thing sitting in front, sitting in front here? I'm talking about current as a function of time. Well, let's look up here. When I talk about charge as a function of time, I called the Q max the charge amplitude. What would be a good name for the thing sitting out in front for a current as a function of time? I max is the current amplitude. And it relates like that. So this is kind of cool. Now, what we've just found out is if you can tell me either the current or the charge, I can figure out the other one using this relationship. So to be clear here, I'm going to call this one current amplitude. This one right here is charge amplitude. And what is the name for this thing again? It's a special angular frequency, isn't it? It's the one angular frequency that this thing tends to oscillate at. It's called its resonance frequency. Now, I'm going to put the word angular in parentheses. No one calls it resonance angular frequency. Everybody I know gets lazy and just says resonance frequency. But you have to know that omega naught means something to do with radius. Or with angular quantity, not hertz. All right. There's something else I want to say. All right. And I should be clear here. These things right here, these conditions, we were using these all together, right? So now keep in mind, if you use cosine for the charge, you're going to have to use sine for the current. Agreed? Because they're 90 degrees, what's called out of phase. Or we saw that, right, it takes 90 degrees or a quarter of a period to rotate from one to the other, so to speak. So basically, one is going to be a cosine wave and the other is the sine. They can't both be cosine. So far, so good? Yeah. What do you think? Should we try an example or not? Or do you want to take your break early and then come back and do example? Do example, then break? All right. We're going to do 31.1. Zoomers, any questions before I start messing up the boards?
So far.
Okay, so you've got all this information. We're going to try and use this information to analyze a real circuit. There's a couple of weird little tricks. I know it may seem odd, but I'm going to actually use numbers for this next problem for a reason. And you just got to have a little faith. It's going to be, all right, just trust me. So you can start reading it. you can start working it. I'm gonna catch up after I erase both boards. 31.1. You're in class here. Do you guys want me to, it doesn't matter as much for the Zoomers, but do you want me to start the problem here and leave this board up? Or, but then what do you want? Or do you want me to erase this and just get to work?
Erase it, let's get to work.
Okay, that way you can see the whole problem laid out left to right without it being as confusing.
Correct. That way we
Yeah.
can't do it much.
Yeah. Okay, you got all that shit written down.
Okay.
All right. All right. So we actually have numbers for once, like in like a month. It's like the first problem with numbers in a month, right? Is that 20 micros? What's E?
24.
24, thanks. And then L is 10 milli?
Yep.
Thanks, that's just a little bit easier for me, I appreciate it. Henrys,
Oh, that's right.
it's such a weirdo unit. So if you're curious, you could read about the scientists that Henrys are named after, right? Sort of like Farads are named after Faradays, it's like whatever. I try not to care too much about those names. This is a pretty obscure reference, but I'm going to bring it up. I think it was Agnes Pockels was mentioned in workbook volume 1. I don't know if you guys remember this one, the oil drop experiment
Oh, yeah.
and Langmuir troughs and stuff. But my thought is, basically, a bunch of old white dudes got their names on the units, and that's, you know, it was kind of an exclusionary environment back then. So I kind of like, you know what? They were probably great scientists. Well, they were obviously great scientists, much better than me. But the fact that they get their names on it, does that really mean that much? So I don't care. So that's my thought. Cool.
Very vested insight.
Yeah, I mean, Gauss, I think about Gauss, like Gauss was a monster, right? Or Euclid and Riemann and all these, but yeah, there's so many other people that, yeah, don't get mentioned. So whatever.
Yeah, poor kid.
Yeah, and just think about poor Beal Savart. Just messing with you, Jay. Biot Savart. Biot Savart. Okay, anyways, yeah. All right, never mind. Okay, let's get to work. Good enough on Henry's? Sorry about the digression. Okay, maximum charge. Q equals EC. Let's get a number for it. E is 24. That, do you agree that's just 480 micros? Because I got a micro and then I got a farad volt. A farad volt is a coulomb. I think that's it, right? And maybe just to clarify, I'll underline that sig fig. We'll make the chemist happy.
Yeah.
All right. What was part B? Oscillation frequency. Remind me, what am I trying to figure out? No. What does frequency mean? What letter does frequency represent?
Omega.
No, that's angular frequency. Oh, strictly speaking, F is resonant frequency. Now, if you had answered omega naught, I would have actually even given you credit on the test because I kind of use omega naught and F interchangeably for the most part. So I just wanted to point out F naught would be resonant frequency. Omega naught is angular resonant frequency. So generally speaking, when you are in this section of the class, we all have to kind of be mean and ruthless about, did you mean this or did you mean that? What do you mean? The main difference here is, what are the units of this one? This one, sometimes it's quite painful. It's hertz. Or sometimes it's 1/seconds. Sometimes you'll see other people write seconds to the -1. Sometimes you'll see other people write cycles per second, old school. All this has 4 different ways of writing the units. What about this one? It's pretty rad. Radians per second. Right? Everybody cool with that? Okay, what is the relationship between these? Does anybody remember? Oh, so you mean in physics 1 when I said memorize this and never forget it, it didn't work?
Nope.
Do you see it now? Do you remember it now? You remember that? We did that all the time and whatever. How does it relate to the period? You remember that?
Oh, okay, that looks familiar.
I said memorize this and never forget it, which never works. So, okay, so the idea is the frequency, the period, or whatever. So all of these terms are related. So I think it was Julie's talk where you were talking about amplitude and period the other day, right? So that was the foreshadowing I was hoping for. That was a good job. All right. In any event, which one of these do I know? Or do I have an equation for? Omega naught equals 1/√of LC. Do you agree once I get that, I can get the rest of them? Let's just figure them all out real quick and let's do the math. What do you get, 2236 for omega naught? Calculator. This is one of these ones where at some point I'm going to get you on this problem. I guarantee. You just got to trust me. Think you know everything, right? So you just got to trust me. And by the way, try practicing using the EE buttons. So when you see the prefix, grab the right EE, right? So it's 1 divided by square root of L is 10 EE -3 times C was 20 EE -6. And so the idea is if you get that EE button down, you're not constantly having to deal with the prefixes. I got 2236, right? What are the units again? Rad. This is rad, man. Okay, 2236. So how would let's go ahead and punch in F naught. That's going to be that divided by 2 pi, right? Divide by 2, divide by pi. 355.9. Hertz. And what's the period? Just because we can. So isn't that just 1 over that number? See that? The 2 pi's would cancel, so it's just 1 over. I got 2.810 milliseconds. If I did the rounding right, I think so, right? Help me out here. Why am I writing 4 sig figs on these numbers when all of these numbers have 3? What is the point of that? So I don't introduce rounding errors in the next few steps. I know this is old school, but I'm bringing it up. So sometimes what I like to do, as you know, is indicate these are only valid to 3 sig figs. for some reason, I find that even on, I'm pretty experienced writing these problems, working them out. You know me, I'm a physicist. I tend to do everything algebraically. For these problems, I have a tendency to do even these problems numerically on test day in my answer keys. So I don't know what that says, but for some reason, I feel strongly that sometimes these problems are easier with numbers. So that's why I'm showing you it this way, okay? It's better to do everything algebraically, except sometimes these ones. That's all I'm saying, okay? Enough said. All right, so let's go to C. How do I get the current amplitude? What's the symbol for current amplitude? Okay. What's the equation for it?
Omega naught N.
Let's pump it in there. Let's get it. What do you get? What was it? Q max. Do you agree this is Q max up here? I should have labeled it Q max. I apologize. Q max is 480 micros. So 480 E negative 6 div. What the heck was omega naught? Oh, 2236. Okay, and so, geez, I guess I'd have to, did I do that wrong here? Oh, I was supposed to multiply it. Whoops, thank you. Times 2236. 1.07. And I guess we should keep extra sig figs. 1.07. Generally, with a first digit of 1, you keep an extra digit. And since we want to keep an extra one to avoid intermediate rounding, we might keep an extra one. Right? So here, this one, I would say we should keep the 4, so let's keep one past that. All right.
Oh, so it's we want an extra one.
If the first digit is a 1, right? This is basically a 3-digit number. You see what I'm saying? Effective from a percent difference standpoint. If you do the math on this one versus 0.999, well, 0.999 is a 3-digit number. This one's almost effectively the same as a 3-digit number from a percent error standpoint. That's why we keep the extra digit on the ones. All right, good enough? Yeah, and maybe I'll highlight this in red since I did it there. Okay, and here. All right. So we found the current, right? We did not find the current. What did we find? Current amplitude. I'm emphasizing that for a reason. This is not current. This is current amplitude. Okay. What's next? No. Gee, I wonder what the next part is. So we're supposed to get current as a function of time. All right. So current as a function of time, this is current. Well, in this case, tell me what I should write down. Does the current start at a maximum or does it start at a minimum? It starts at 0, right? So in this, I should be careful. Do you agree we start out with the capacitor having all of this? So that's going to be Q cosine. The current should then be I sine. Agreed? That's what it should look like. Now, which way is current going to flow initially? Do you agree this is going to be, this is the initial state. This is where the picture comes in handy. The capacitor, when we shift it to position B, when this goes into position B, which way is current going to flow? Clockwise or counterclockwise? That way, whatever way that is. So in this case, this equation is valid, and we could just add it's going clockwise. If for some reason you wanted to define it as counterclockwise, you could just put in a minus sign. Do you agree? Negative this counterclockwise is equal to, so that's what I mean by the polarity, who really cares? Right? A negative counterclockwise current is positive clockwise current. All right. Are we supposed to plot this thing? Huh. what's going to be a very useful parameter that we see on this whiteboard for helping us make the plot? What's the key thing that we might start with? Okay, what's the next good time?
Max.
IMAX.
Okay, when does that occur?
T equals 0.
What's the key piece of information that tells us how long we need to plot?
Period.
The period. This is where the period comes in. If you're ever curious, like, what's my delta t need to be in my simulation I'm running, or whatever. If you know the period of motion or some sort of time scale, or if you know what tau is, right? Usually there's some parameter in a physics equation that talks about time. You can use that to get a feeling for how big your time increment should be. So here, if we want to analyze this, how about I go out to time t? And somebody said, is it okay if I just round this to say 2.8? All right. And then when we're trying to make a sine plot, how should I split that up? Into how many pieces, how many chunks? I think that's what you were saying, Jess. Or no, was it you, Christian?
4.
4. Yes. Right? So it's easy to split something in half
Periods, got it.
because there were 4 chunks of time that mattered. And so it's kind of convenient here that we have this number. What's half of that? 1.4. What's half of that? 0.7. And in between with the 2.1. Is everybody okay? So when you're trying to understand these, this gives you an idea of the times. And so if you were going to make a plot of this, you'd want to use something smaller than that, right? Okay, all right. So now it's going to go from here to up to here, to down to here, to down to here, back up to here, and you can kind of sketch it, right? And then what are we plotting here? I in amps. And what's the peak value? About 1.07 amps. And what's this minimum value here? Negative 107, right? So was it Niles earlier that said plot it? Or, oh, okay, yep, we got our plot finally. I feel like you can really get to know something by plotting it, right? Hello, Kurt, we can be good friends now. Okay. Ooh. All right, I feel like we did part D. You ready for part E? All right. I'm going to shift this over here. We're going up to part E. Zoomers, any questions on this board before I move away? Good, okay. Oops. Here we go. So part E. In part E, we're supposed to get what time after t equals 0 do we first get 90% of max current? That's basically the question, something like that. Something like that. Any ideas what I should do? Yes.
Use the function time.
Use I of t equals I max sine of omega naught t, right? How could I use that? Now, there was also a comment that we could use the graph, right? Let me bring that up here. The graph is excellent for getting an approximate number to check your value. Do you agree? The graph has merit. Estimate it. Just kind of eyeball it. Here, just come up here and point where you think it is, and then we'll pick a number, right? All you got to do is point to the, where does it first hit 90% of max in your opinion? Right about there. I agree. Right here, right? Let's give him a round of applause. Actually, that's pretty darn good.
Yeah, well,
All right. Okay, so do you agree? We're looking for a time that's probably like 0.5, 0.6 seconds, something like that? Or wait, this is not in seconds, is it? It should be milliseconds. I made a bad mistake there. We probably would have caught that in the next step, but the time was rated in milliseconds. That's why we chose that time of milliseconds. Okay, so now that we know the approximate value, what are we gonna do? Tell me what to do. Anybody?
Set I of t to 0.99 max.
Yes,
And
that's what you're
self-return.
saying too, Jess?
Yes, sir.
I agree. Then what? Okay, so then what?
Inverse sine both sides.
Okay, tell me what you get for your number. Punch it in. Well, don't we know this? I can divide by omega naught, right? Has the right units, check. Go ahead, punch it in. Give it to me. I'll do it too. What was it? 2236 was omega, I think. Omega naught. I got. Is that what you got? Punch it in on your calculator, please. Make sure I didn't screw it up. What are you getting, Jess?
0.0286.
0.0286.
Was 2 degrees.
Do you agree? We know this answer's got to be right,
Yeah.
but you can't find your error.
No.
What is it?
2 degrees.
Degrees.
It needs
Yes.
to be in radians then.
Do you agree? This sucker's in radians
Yeah,
right here.
radians are- oh, that
Aha!
makes sense.
This was the one I was hoping to allude, right? I wanted to talk about this part right here. We kind of lulled you to sleep and then stung you with the old degrees radians mode. So here,
Okay.
now you're gonna love this. Now, this is in the solution if you didn't notice. So if you forget this, it's in there. But this is the annoying part. And now for the rest of class, we're constantly going to be fighting with degrees and radians, degrees and radians. And if it's as if it can't get worse, we're going to learn there's a thing called a phase angle. Omega is always given in radians per second. The phase angle is always given in degrees. And so we're going to be writing things that look like this. Sine of 2236 radians per second times time plus 36 degrees. And you're going to have, this is the standard way as well. I'm not making this up. It's because of something I don't want to talk about. Electrical engineering. All right, so it turns out this is just people think in degrees, and you'll see why. It makes it easier to communicate. We'll discuss this weird problem later. Okay, phase angles and why we're going to use them in degrees later. All right, just humor me for now. All right. Part F. So I think we did this now, right? I think we're done with that. Let's get to part F. I want the magnetic energy. What's the equation for magnetic energy? Anyone recall?
UL equals 1/2 Ly squared.
Is this good for the maximum or for a function of time or both? Both. Do we have the current as a function of time?
Yes.
We do, don't we? It's 1/2 L. What was the equation? I was I max squared, sine squared. Do you agree we have to square both the amplitude of the current and this, and remember the 1/2 L? At this point, I'm confident you can plug in the numbers. This was the one I was trying to trick you with. All right. Do you agree you can plug in some numbers here? Okay, let's keep going. How about part E? Oh, wait, G. Electric field, what would that be?
Q squared over 2C.
Okay, so UC is Q squared over 2C. Do we know what Q is? Could you tell me what Q is? Why? What's our general formula for Q of T? Q max sine or cosine. Well, if the current starts as a sine, and you know there's a derivative or integral, that tells you this one must be a cosine. But how do I relate Q max to I max? Do you remember the equation?
Differentiated.
It's the one I screwed up earlier, right? I'm going to spend a little bit of time on this one. Wait a minute. It's almost like I could divide here like that. Do you agree Q of T should equal I max over omega naught cosine omega T? Right? And then I could square this and put it in there. Let's do that. I know this may seem a little bit silly. Wait. I'm going to get a 1 over 2C. I'm going to get an I max squared over omega naught squared cosine squared. Right? Gosh, I just wish, wait a minute. What is this thing? Yeah, what was that?
Oh, that's
What if we plug that in? If I plug that in, don't I get an LC up top that cancels this C? And then I get exactly the same looking crap with a cosine squared? Isn't that beautiful? This ends up being 1/2 L I max squared cosine squared. This is important to note. When you have a pendulum swinging back and forth, do you have more gravitational or more kinetic at its maximum? If I have this pendulum swinging back and forth, is there going to be more gravitational or more kinetic at the maximum? Shouldn't the maximums be the same? I convert all of the kinetic into potential or vice versa. They have the same. This is UL max. Right? Do you see it? But that's also UC max, isn't it? So the maximum energy, the energy amplitude is the same for both this one and for that one. That's kind of cool, but that makes sense. We should have more energy oscillating the capacitor than we do in the inductor. That'd be like suddenly I have extra energy from somewhere. Oh, that's cool. All right. Is everybody good with that? All right. What's the total energy going to be? What do you get when you add this plus this? You get the total energy, right? What happens when you add sine squared plus cosine squared? 1. It's a constant. Let me show you now. I'm going to go to graph land. All right. You guys can work it out. If you want to add them up, do it. Let me see. I just have to think carefully when I'm screen sharing so that I get the right one. Okay, let's do this. Sorry it's taking me so long here. Isn't this fun? I find this very interesting. So very into this kind of thing. Let me share screen. Which one? Let's do this one. Sorry, sometimes the Zoom locks my brain up. All right. Give me a sec here. All right. So Zoom, you can see the solutions, and people in the audience, you can see the solutions, correct?
Yes.
And then maybe I'll move this out of here, just, oh. Hey, if you guys want to wave to the class, they can see you. They're looking at the, yeah, all right. If you've had enough Zoom in your life, which I'm sure, yeah. So that's what, watch out for that radiance. Oh. Okay, so here's the idea. Oh, it looks like in the solutions, I added them up using the capacitor formula, but basically you get the maximum energy is the total constant energy. Let me show you the plots here. We'll come back to that. Oh, I need to go to a slightly. Now, oh geez, Zoom. Sorry guys, you're out of here. All right, so now you can kind of see this. Sorry, this is. All right, I guess I'll annotate so they can see too. Let's focus up here on this plot. I want to focus on, notice this important fact. There's two vertical axes because it doesn't really make sense to plot charge and current on the same axis. So in this technique, what you can do is you can label one set of axes for the current and then the other for the charge. And notice I chose to use millicoulombs for, I guess this just happened to make the numbers look about right. So that's why I chose it this way. Apologies. But notice there's different scales here. But now you can kind of see things a little bit nicer. We see that this one is Q cosine, right? And the red one with the dashed line is I max sine. Do you see that one's the sine and one's the cosine? And notice, what was the period that we were expecting? 2.8, right? Do you see that that's 2.8 milliseconds? I don't know where I labeled the time axis on here. I think I mentioned it in the picture, or maybe I just forgot. Whatever, but yeah, you can see the time is supposed to be time in milliseconds, so apologize for that. I should have taken off the grid lines. Do you agree? It's too messy. I'm a bad person. And my grid line, whatever. Let's not do that. Yeah, it's totally inconsistent. Do you agree? So I don't know if you noticed this. I had a student earlier say, you know, you really care about that. It turns out I don't really care about that stuff at all. I do it because I think it's going to help you transfer. I hate all that formatting crap. But I do it because I know as an engineer, you have to kind of have that attention to detail mindset. So believe it or not, that is not my passion, critiquing formatting. But I do feel it's important for you. All right, that's why we do it. All right, so notice the energy oscillations down low. It's a little bit different there. Do you see that? The energy oscillations, I only need one axis, but notice the total energy is the same as the max. That's U total, is this line going across the top. Well, that's the same as the max inductor energy. It's also the same as the max capacitor energy. And the idea is it just keeps changing forms. Conservation of energy. Do notice something subtle. Do you see the energy oscillates at twice the rate of the current or the charge? You see the bumps happen twice as often in the lower plot? And I like to point that out. Remember that cosine squared, look at this 2 omega t, twice as rapid, or sine squared has a cosine 2 omega t. So an interesting thing, we say that the energy oscillations are twice as fast, right? The cosine squared function oscillates twice as fast. That's the same thing as capacitor fully energized with positive polarity, capacitor fully energized, negative polarity. And then so that's why it happens twice per cycle. Is everybody cool with that? Now, while I've got this up, I know I'm putting you to sleep here and I know it's been a long day, but I want to show you something else. Is that big enough? I have been kind of dodging this for a long time. It's finally time to get to it. So in this case, look at this cool analogy. A lot of you are probably saying, I'm never going to do these kinds of circuits in my life. I would agree with 90% of you, maybe even 95. However, I spend time on this because the physics behind oscillations in physical space, like mechanical engineering, civil engineering, physics, modern physics, quantum mechanics, any kind of oscillation you can think of that's mechanical is directly analogous to this. So, for example, if you think of position as charge, what's the derivative of position? Velocity or current, right? So we see the analogy holds. Force, electromotive force. Thank you. I was blanking there for a second. EMF is like a force. It's got it written in the word. Mass is inductance. Think about this. When you have mass, you resist changes to your motion, right? Mass, you resist changes to V. Inductors resist changes to current. It's the same thing. Isn't that cool? Now, here's where it gets a little bit weird. I want to point out these equations down here. Spring potential energy versus electrical potential energy. You see that 1 over C has to be K, right? So there's actually a term for this, and I forget what it is, and I don't care. Right, drag force, right? Ohm's law, drag force, same thing, kinetic energy, magnetic energy. So it turns out, my point is this. If you learn the math here very well, this relates to all branches of engineering. We have suffered and suffered and suffered this semester to get to this point. We're going to start rocking this hard and just keep seeing all these interesting things that relate to oscillations, which I argue oscillations in general is one of the biggest principles in all of physics, in all of engineering. If you're a civil engineer, you really need to find out what the resonance frequency of your bridge is so it doesn't fall down in an earthquake or a building, right? So it's like every piece of, all right, enough on that. Let's take our break. It's hugely important. Any questions? It's kind of cool. Zoomers, any questions?
Oh, they're pretty cool.
I think that's beautiful. All right. Okay.
Chemistry uses right resonance too.
Let me see. How do I get out of that? I need to, oh, that's right. I need to do this. Sheesh, I'm lost. Pretty amazing. What'd you think? cool? Is it starting to?
Yeah.
Yeah, gradually by the end, it's like after you finish this course, you're like, oh yeah, now it makes sense. Too bad it didn't make sense on test one, right? I know.
Yeah. Beginning is like, oh, it's current.
Yeah, right?
No,
Don't forget to stop the live stream, by the way.
What's that? Oh, yeah, yeah. Thank you. That helps find your way in the video, right? Thank you.
Yep.
Good day. Welcome to the Great White North. I've got my toque here, eh? That's what we call the stocking cap. Get your toque on. All right. I think it's time to get going. Is it I have no idea. I lose track of time all the time. So I want to point out something. We just did 31.1 and it looked like this. I think there was a resistor here, a capacitor here. And then there was an A and a B and a switch. And then
Interested.
Yep.
Did we mean to switch the board?
Oh, thank you. My bad. That board. So that was 31.1. I want you to take a second to look at 31.2. Compare and contrast, see what's different.
What's up with that switch?
You see, do you agree that the switch looks a little weird?
Yeah. Like, oh, is it off on me?
What's in the middle now?
Oh, the inductor.
And then the capacitor's over here. So all the numbers are the same. Do you agree?
Yes.
It's exactly the same set of numbers. It's the same 24 volts, 12 ohms, 20 microfarads, 10 millihenries. Now, in this case, there's two main differences. The AB switch is different. It's a sliding switch. Why? Here's the tricky part. When I put this into there and charge it up and then disconnect it, the charge doesn't magically disappear. Agree? But you can't really do that with an inductor. How does the inductor store energy? In its what? Electric field or magnetic field? Magnetic. Is that current or charge based? Current. So if I'm starting over here in A and this thing's energized, and then I try and go to B, if I have to disconnect the circuit, what's going to happen? It's going to spark and then turn off, right? Like the vacuum cleaner, right? It's like, it would be like trying to take the vacuum cleaner, pull the plug and move it to a different plug-in, right? You're going to get this big spark, but so the idea here is this switch is a specially designed switch so that physics students can still do the problem. And the idea is basically it's connecting to B at the same time that it's disconnecting from A at exactly the same moment. Cool? Now, in practice, what does this mean? Right? As long as you switch it very quickly, it's not a big deal, right? And so the issue is, if you're switching this over here and you take a long time, the capacitor could charge up off the battery instead of off the inductor, and that might screw things up. So we're going to assume that you can do this so quickly and it's a perfect ideal switch, and it doesn't really work this way, but yeah. Now, other than that, we got the inductor stores magnetic energy. So we're starting this here. What's that going to mean? Remember over here, we had Q as a function of time and I as a function of time. This was Q max. Was this cosine? Which one was this? This one's cosine. How do you know it's cosine? It starts with charge, it starts with cosine. So that meant the current was. So what do you think is going to be different over there? Like that, right? So that's a major difference. So let me ask you this. If we keep all the numbers the same, do you think we're going to get the same values for Q max and I max? What do you guys think? Yeah. So then if I'm asking it twice or three times, what's the answer?
No.
No. Isn't this interesting? I want to point something out. Does the resistor matter significantly in this LC oscillator? No, why not? We charge up the capacitor and then we take it out of the loop and it never matters. In this one, why does the resistor matter? How does that help us figure anything out? If you leave this in position A for a long time, how does the inductor behave? A short or a break? Those were the terms we used. Or does it behave like an open switch or a closed switch?
Short. close.
Short, yeah. So do you agree the current initially in this one would be? Two amps. What was Imax over here? It's not the same. Isn't that interesting? I had no idea what I was thinking about it. I'm like, this shouldn't, when I wrote these, I'm like, it'll just be the same. And I was hoping you would notice this. I'm like, wait a minute. I forgot about the fact that the resistor matters in this circuit because it sets the Imax. And it doesn't matter over here because it has nothing to do with Qmax. So in general, it's not like this current's always going to be higher. What if I had used 5 billion ohms? Wouldn't Imax be really tiny? So this number could literally be any number, bigger or smaller than this number. It's not, yeah. But what about omega naught? Is that going to be the same in each circuit? Yeah. Because that's given by. So, all right, that's cool. Now, what's a practical application of this system here? Lc oscillators. Can you think of it? Like, here's an example of an Lc oscillator. Here's an inductor, and here's a capacitor, right? This has got some plates. Whoops. All right, so I don't know if you can see those at all. Let's bring it into the Zoom, right? Can you think of any practical applications of these? Maybe. That could totally be valid and I wouldn't know. All right, so, but here's an inductor, here's a capacitor. When I connect these together, they oscillate at a certain frequency. Let me ask you this. Let's say I wanted you to send me some information at a certain frequency. Do you agree I could take this capacitor and this inductor, which has various taps on it, and the idea is I could get a certain value of L and a certain value of C, and I could dial in any specific frequency I want, or angular frequency for that matter. Huh. What's a device?
Radio?
Radio. This is a radio. You put these together, the Lc oscillator is a radio. Or you could think of it like a cell phone, right? In a way, right? There's some sort of resonant frequency that you want to tune a signal to. So the idea is, think about this now. We haven't really discussed this yet, but imagine I'm an EM wave, an electromagnetic wave, and I go through this loop. I'm going to induce, right? If I'm an EM wave, there's a changing magnetic flux. This inductor is going to pick up on that, and I can then use this as a pickup coil for that magnetic field. I'll have magnetic energy, and I can oscillate. And so it's a lot like a swing, like a kid on a swing, right? There's a certain frequency you can push something, right? And if you push at a certain frequency, the swing oscillation gets more and more. The idea is you could drive this thing with a radio wave, and the oscillations will get picked up to the point where you can do it. So last time I was in lab, we actually did this where you turn these into a radio. And if you don't know about this, there's some weird stuff they used to do with these stones and things called cat whiskers, and they'd touch a rock in a certain place and blah, blah, blah. It was basically, they were making a diode. So this plus a diode can actually, and then you can put an earphone in it. So these two things plus a diode, maybe something else, but no battery, you can literally pick up AM radio signals. And we would jam this out in the physics lab. Just be like, yeah. It was always like, just kind of a fun lab, but this time we have a holiday, so we can't do it. So that's the way it worked out. If you want to build these, just look up Quaker Oats radio, buy the crap or borrow the crap from me. But the idea is you use a variable capacitor and variable inductor, and you can tune the different frequencies, different radio stations. If you're curious, which I know you are, look at problem, page 226, problem 33.6. If you're curious about the AM radios, right, there it is. That's the radio range of frequencies, and you could see, oh, okay, you could get your frequencies from there. That would tell you about the inductance and the capacitance. You could use a meter like this. This device is an LCR meter. I forgot to bring the cables. I'm so dumb. But you can literally plug this in, it'll measure L for you and C for you. And how do you think it does that? How do you think this thing can measure currents? What's that? Magical fairy, it's close. It has a little oscillator inside of here, right? And so if you know, like V sub L equals L di dt, you can apply a little oscillating current, read the voltage, and then you can figure out the L. Or if you know that, what is it? I equals C dV dt, you can oscillate it and you can put in a little oscillating current and read the voltage or whatever, and it relates to the capacitance, something like this. So I suspect that's how it's working. It has to do something with this derivative and the fact that omega keeps popping out and LC is in there. Anyway, so that's how you can analyze these things. Here's a fun question for you. I'm going to pass this around, but I'm going to show the people on Zoom here real quick. That's maximum zoom. All right, so I don't know if you can see this. I have two coils of wire here. The same number of turns, the same radius, the same area, but one of them is high gauge, narrow radius, and the other is small gauge, big radius, big cross-sectional area. So I'm just curious, which one do you think has more inductance? Do you understand the question or the demo? I'm going to pass this around. I meant to include the cable so you could actually check it. I know the answer. So I'll show you here real quick. This is just for fun. Oops. So the idea is I have a pipe here. Right, and in this case, the idea is some of these have very, and some of them have very fine. So the idea is you have a thick cable versus a skinny cable. You wrap it the same number of times. What's your gut tell you? You'd all think the thicker, right? So what do you think the answer is? Yeah, it turns out this one was something like 1.8 millihenries. And I forget this one was like 3.2 millihenries. Now you might be saying, why? The idea is the skinnier cable, you can pack the coils closer together and the flux from each ring can affect the other rings more effectively that way. So the tighter you can wind it, the more inductance you get, right? Think about this. I don't think you'd have any trouble saying if I did a loosely wound solenoid with 3 turns versus a tightly wound solenoid, right? Even if it's the same area. The idea here is this coil is going to have less of a flux through this one than these coils that are literally right on top of each other. So that's just kind of a fun puzzle on inductance for no good reason. I don't know why I found that in the lab today. I'm like, oh, I should talk about this today. It's kind of cool. Just throw it over. Thanks, boss. Fun little puzzle there. It'd be more fun if you could have measured it, but I didn't measure it today. All right. That's a scary look. Been dreading that next part. All right, I want to talk about something else before we get in there. It's important because it's in the next topic. All right. Okay, so I want to talk about a new concept called a phase angle. This is something I glossed over. I don't know if you noticed this. I allude to this a little bit on page 195, I think. So, all right. We could actually write one equation to rule them all. And I vaguely referenced this earlier, and I've got too much red there. So I can get that out of here. And maybe just to make this pop, let's see if I can change the color on that. I like that light blue marker for some reason today. You guys, is the light blue working or not? This one right here. Good enough on line 2?
Yeah, that's fine.
Okay. So phi is called the phase angle. Now, at first, you might have no clue what this is. if you were going to try to understand what the phase angle is, any ideas how we might understand that? What do you think? What's
A
that?
shift in the start of.
Oh, what were you going to say?
I was just thinking like it's a shift in the start of like how the
It is a
how the
shift in the
graph
start.
starts. I guess.
It's a shift in how the graph starts, and if you want to understand it, we should plot it. So we're going to do that in just a minute. Now, typically, given in degrees, most phase angles are given in degrees, and I'll explain why. Okay, so in just a second. But watch this. Q initial. That's t equals 0, right? If I will set t equal to 0, what do I get? It's Q max cosine of the phase angle. So essentially what we're saying here is, if you have a plot like this, if you tell me the phase angle, right, it's a multiplicative factor that tells you where you start in the cycle. It could be positive or negative, right? So you could have something that looks like this. And the idea is this point right here is Q initial, the initial value. So the phase angle is simply a term that helps us decide where you start in an oscillation. That's it. Good enough? Okay. Now, if you're really trying to understand this, let's make a quick plot. So let's turn this on. I'll make a plot. Let's play around with it. How are we doing on time? We're doing all right. Okay, and then whoops, I need this one right here. And then I'm going to need this right here. Okay, I need my Zoom right here to share screen. All right. So let's do some general strategies. So there's probably going to be some amplitude. How about we just call it Q max? And let's forget about the units. Let's say it's just, how about 420? No. And then, was that what we had in the last one? I don't know, if not, it's fine. Okay, so then, and then we need some kind of a omega naught, right? Omega naught. So, and then I want to be clear here, just because this is something that matters. Let's be clear. Normally, we're going to talk about omega naught in radians, right? And then over here, we could do phi, the phase angle. Typically, it's mentioned in degrees, but then we're probably going to immediately want to convert it to what? Radians, because Excel is going to use radians calculated, right? So let's pick an omega here. Give me a good value for omega, any value. How about like 200? Sound good?
Okay.
All right. Now let's start with 0 degrees phase angle. So how can I get this converted to radians? Remind me.
It's radians.
Equals radians, right? Yeah. Okay. Now I need to make a plot. So do you agree I'm going to need a bunch of times? Okay. 0 is the first one. What should I use for the next one?
Oh.
I have no clue. Right? I know you're tired. It's not gonna, you can rest. Trust me, it's fine. But this is one part I wanted to kind of point out, because this can be kind of frustrating for students, is how do you pick the right time step? What is our time scale in general here? How do you figure it out? Period. How do I get the period? 2 pi over omega naught. Yeah. So, aha. Now I know if I go by 0.1s, that's going to be terrible. Do you agree? So now in this case, maybe I should go by 0. What? Pick another number. Well, if I go by 0.02, it's only going to take two time steps to go past the period.
0.001.
Yeah, or something like that. How about we just say it's, we say the first one's 0, we say the next one, how about we just say dt? And we just say it's equal to this divided by 100 maybe, so we get 100 steps. So how about we say 0 and then 0.0003, just because that's a nice number, and then maybe I don't like that, so I'll just round it down to 2. Right, so now I've got a nice time step. Gee, it would have been nice to use a different time step, but this one should work. How far do I need to go? To about 3, right? What was it, 0.31? Oh my gosh, do you agree I probably could have used a larger time step? But whatever. So now if I want to get Q as a function of time, right, this should equal, what's the equation I want to use now with the phase angle? Do you remember? It was Q max cos of phase angle, right? So I like to have that equation sitting there. So in this case, it's going to be equal to this. I hit F4 times cosine of omega naught is this. Do I need to make that a constant or not? Yes.
No.
Right? Because omega naught, there's only one resonance frequency. The time is changing. What is that? A5? Plus, which phase angle do I want to use? The one in radians, even though we're going to talk in degrees. And I'll explain why as we do this. All right, so as I do this, let's fill this down, and hopefully we did this about right.
You wanted the phase angle to be a constant as well, right?
Oh, yes, thank you. Sorry, you're right. You mean right here? It works this time, but you agree the phase angle should be a constant? I apologize. So this is why it would have been nice to use name cells, agreed? If you name the cells, it automatically remembers it's a constant. So in this case, that's fine. And let's plot this dumb thing. All right. Insert. Finally there. Now, that's cool. An interesting thing, watch what would have happened if we would have done 0.01 and just done this, right? Well, wait, just give it a minute here. Right? If I do this, let's see what we get.
Yeah.
Notice, does it look like do you see how it's a sine wave within a sine wave? It's because we're missing the peaks, right? So if your time step is too large, what if I had done 0.005? I know this seems like a waste of time. I just want you to know like the kinds of errors that come up when you're making these plots so that you can know how to fix them, because we're going to do this in lab. See how it's still not very good? The peak is, the idea is when you choose a bad time increment, you don't necessarily hit the peak every time. And so you get this numerical artifact that looks like it's basically aliasing. All right, so now I'm going to try and go back. Is that it? Okay. Finally, let's get these grid lines on. Well, in this case, what's a good set of grid lines for this one? Oh my gosh, come on now. Well, what's a good set of axis points on this one? What do you think? We're fine here. We could go up to say 0.32, right? You see what I'm saying? Why is that a good choice? Because it's almost one full period. What about the axis? What about the major units? What's a good choice in this particular case? How many chunks do I want? 4. So what's approximately right? 8? It's not exact, but you agree that's pretty close? And then we can get rid of these, and then we can put some tick marks just so I don't get lost. Oh, whatever. Let's leave the grid lines on for once. All right. So in this case, fine. Now, out of all this, this was the point. If I type in 90 degrees and hit enter, what should happen? I'm going to change the phase angle by 90 degrees. What happens?
Become like a sine wave.
Oh, which way did it shift it? Maybe we could see better if we just use 30 degrees. When I type 30 degrees, watch what happens to the curve. Ready? Which way did it move it? Yeah, isn't that interesting? So if I'm adding, okay, so if we go 60 degrees, it's gradually moving it, but notice that 90 is like a quarter of a 360. A 360 is a full circle. This is why we think of phase angles in degrees. 90 degrees is a special number to change it from sine to cosine. Most of us don't think, oh, 1.57 radians is a quarter cycle. Now you probably do because you know it's pi over 2, but you'd have to sit there and think a little bit. So this is generally why we keep phase angles in degrees, or 120, right? Oh, jeez. How about negative 90? What's that going to do? Makes it a positive sine wave. So depending on the positive or negative phase angle, that changes your cosine anywhere. So this is why sometimes people write this with phase angles, because you can write cosine omega t plus a phase angle, and you can get sine waves, cosine waves, or any starting point in between. That's what I was trying to get at with phase angles. Is everybody okay with that?
Yeah.
All right. So let's foreshadow the next torturous lecture. All right, just very briefly. And let me see. Oh gosh, I need to do this button. That's right. Not used to that. I get so used to it. Whoops. Okay, this one. And you could turn now. You know how I usually write up a page of notes for you, right? Look at page 199 and then flip the page to 200 and realize, uh-oh, it's big time. Yeah. I should really scare you. But I just turned off the display. I should have had it when I was on there, right? One of the most frustrating things I think here is coming up. We're going to be talking about AC circuits. AC circuits.
Gotta switch the board again.
Thank you. This one. Thanks. I appreciate that all the time. On the weekends when I've gone in, I've made it like 2 or 3 times in a row where I've forgotten to change the board and had to stop and start over. Like I was just like screaming, cussing at the whiteboard. Like, damn it, why am I wasting my life on this stupid class? So yes, I do know how you feel. All right, help me out. A DC circuit. DC means direct current, right? What's the principle? Give me an example of a DC circuit that you think of. Battery, maybe a resistor, right? That's a DC circuit. All right. AC circuit, what's the difference? The power supply is different. This is an AC circuit. All right. So the main thing here is the voltage in this case, I'm going to say delta V of the source, in this case, is E. In this problem, delta V of the source is a function of time given by oh, no, that's not omega naught. This is not omega naught. This is omega, and I'm going to explain about this next time. It's one of the most common mistakes. Do you see an LC in this circuit? I don't. So should we have an omega naught associated with an LC resonance? No. Okay. This is going to be called the operating frequency. But you know what I'm going to say next. It's an omega. What is it really called? But what does anybody say? Operating angular frequency. Yeah, so we're just going to call this the frequency, but you know it's angular. All right. What is this? No. Well, yeah. Well, no. Right? If you plug in t equals 0.
Oh, that's true.
What's the name for this in general? What's the name for the thing that sits out front of a sine function? amplitude. So I would call this the source voltage amplitude. It is not the source voltage. Do you agree?
Yes.
And that's what I've been trying to harp on all day long. The source voltage is this. So the source voltage is a function of time, is a func of time. You guys can't have any fun in this world, right? We'll write out function. So watch out for these things. Now, in this case, I know it's about time to go. Here's what gets really, really annoying. What are our equations for voltage across a resistor? Can you remind me? Okay. What's our equation for voltage across an inductor? What's our equation for capacitor? And then we took what, right? Can't we solve this?
Yeah.
But wait. Isn't that? Huh. So what happens here is this. I'm just gonna humor me a little bit. If you put a resistor in here, the current is going to be a sine wave. If you put an inductor in here, it's going to be a cosine wave. Right? Because the voltages are going to match up, and then you're going to have to take a derivative of that somehow. Similarly, if you integrate, don't you also get a cosine? Right? If you integrate, so what happens here is we're going to have 4 different voltages. We're going to have the voltage of the source that's oscillating up and down. There's going to be the voltage across the resistor, which is in sync with the current, which is oscillating up and down. There's the voltage across the inductor, which is oscillating up and down, but there's a lag or a lead to it. Same with this capacitor. So they're all going to peak at different times, and we're going to have to add up sine waves that are peaking at different times. Look at problem 31.11. It's going to look something like that. We're going to have to try and add up all those different sines and cosine waves. Isn't that crazy? And that's not even right, because I forgot something, and I'm asking you to look for it, but you won't see it right away. It looks like you would, it's very complicated. Anyways, we'll allude to this in a little bit, but it has to do with this derivative and this integral changing things by 90 degrees of phase. Do you agree going from a sine wave to a cosine is like 90 degrees of phase? That's going to be critical when we go through this next time. Should we call that good?
Yeah.
Okay. I'm going to send you the pre-videos and you should read. You should watch a video. You should watch the SBC. I'll send you the last, I'll send you everything I got after class tonight. Okay. Yeah. I would highly recommend watching the SBCC video I'm going to send you sometime before lecture Wednesday. It will take your life from miserable to acceptable. Yeah.
I'll take it.
It's probably it's the best SBCC video I've ever seen. Right. And it's a really good video on this topic. It's probably better than my lecture, but yeah, so I'm going to leave it at that. Okay. Zoomers, any questions?
Yeah, good.
All right.
What was that about borrowing stuff from you for the radios if we were wanting to do that?
Yeah. Later. We could talk about it. No lab this week, but we do have lab next week.
Yeah.
Yeah, we could just hook you up and you could take it home and build it and do whatever you want.
Okay.
It's super cool.
Yeah, I'm just kind of interested. It seems cool.
Yeah, it is. It's really it's super interesting to build a radio that has no battery in it, and then you can, you know, you can hear something and it works. It's just mind.
Yeah, sounds cool. All right.
Frequency, right, too?
It's like, yeah, you can tune it by changing the plate areas.
I'm gonna tune it to the Cox frequency.
Yeah, I don't know, yeah, so, I'm assuming, so if, as long as it works by amplitude modulation, that's the kind of signal that this will work on. So I don't think this is gonna work on FM, which is frequency modulation. I have no idea what they use, but this works on AM radio.
If they use AM, I'm gonna try to make one.
Yeah, for sure, for sure. Yeah, yeah. All right, you good?
Yeah, okay, take
All right.
it easy, I'll see you on Wednesday.
Yep, sounds good. Should I stop the live stream here?
Yeah, go ahead. Did you say that if it works on amplitude modulation, then you could get it?
Yeah, it should work, yeah.
But there's probably like a frequency like limit for that, huh? Like how high you can
all that
go?
is changing the inductor and capacitor, and maybe that changes the amount of noise you get, but yeah.
Right. So I don't know. Say you wanted to try and build one to listen to the ATC or something, because that's on like the kilohertz frequency.
Yeah, yeah.
Would you be able to do that with stuff from the lab, or would you need like a lot more material?
No, I think that's probably good, yeah. Now, one of the tricks that you're gonna find is when you're building a radio, I'm gonna go super short. Is that okay? Just go to the board real
Yeah.
quick?
Yeah, that's fine.
So let me get rid of this here. Actually, let's go to this board just because I got it, since you asked here. Do you know any equations that talk about radio waves at all? Anything?
No, not really. I'd have to read about it.
I'll teach you one of the most fundamental ones. Radio
Okay.
waves are essentially the same as light. C equals F lambda, right?
Okay.
Now, why is this important? C is the speed of light. That's 3 times 10 to the 8 meters per second. Speed of light in a vacuum, which is basically the same thing as speed of light in air.
Uh-huh.
Right? Now, you just told me a frequency. What was your, pick an AM frequency?
Well, I guess what, 1440 AM?
Okay?
So what does that mean? Hertz?
1440 kilohertz.
Oh, okay.
So I believe, and I'm just going to look at workbook problem. What did I say it was? I've got it right here. Just give me a second. Yeah.
33.6.
So AM radio goes from 535 kilo to 1605. So that's right in the middle of it. Okay.
Okay.
Do you agree we can get lambda?
Yeah.
Figure it out real quick. Punch it in, will you?
Grab my
I got a calculator too.
right,
What's it gonna be?
3D8 divided by
3E8,
so
40E3. 208.
yeah.
Okay. Now, that's the wavelength of the waves. Now think about this. Is that big or small?
That's pretty small, I think.
How many football fields is that?
Oh god. 2.
2 football fields. That's pretty big to me. So that's long, right? This is why
Okay.
radio signals can go around entire buildings, right?
Right.
So
Right.
that's a huge wavelength. Now, it turns out if you're making an antenna, the classic antenna that you'll see is something like this. It's called the dipole antenna, basically 2 pieces of metal. Ideal lengths are lambda over 2. You could use lambda over 4. But basically, you need a piece of metal that's that long. Well,
Okay. All right.
that's going to be, let's say we're going this way, 50 meters. Approximately, right?
Mm-hmm.
So it helps, you don't need it, but it helps to have an antenna that's 50 meters long. Now, why am I bringing this up? Your AM radio on your car clearly doesn't have a 50-meter long antenna, right?
Right. Right.
But the longer your antenna is, the more efficient it is. And so what we would do is we would take a spool of copper wire and run it between the buildings and try to make sure it was above the ground so people's heads aren't getting chopped off. And right, if you just run a 50-meter long wire, we could totally do that in the lab easy, right? And just string it along the trees and run out the buildings. And then that makes a huge difference in how effective this is for our cheesy little one. The longer your antenna, the easier it is to pick up these signals. And what we found is when we use the long antenna, it works like it's great.
Okay. Interesting.
Cool.
Yeah. So I just used that C equals F lambda And so ATC runs on like 5 kilohertz. So we'd need a 60-kilometer wire. No. We need 15-kilometer wire. So
Now, and do you agree that's, again, what you could do is you could use circuitry to
Right.
improve the performance. So I suspect even if we use like a 10-meter long, we'd probably be good on either of those, but I don't know. But then again, we might need a longer one for the other one, but I don't know.
huh. Okay. Yeah, I was just curious. It's not a big
Yeah.
deal.
Another thing that people do is they'll do tricks like this, where they make different kinds of antennas. Have you seen something that looks like this in the real world?
Yes, I have. Yeah.
Right, and this is like a back reflector, right? And so this is a very directional one. So this is like if you know the direction your signal is coming from and things like that. You could use loop antennas like this and track the flux that way. And then so there's different types of antennas for different types of jobs. And at this point, you
Okay.
know as much as I do, but we can totally try it. We'll put the LC in there and see if we can hear anything beyond noise. We'll put the longest antenna we can stand and try it.
Yeah, I just think it'd be kind of cool to see if we could, I don't know. I know there's nobody at the Santa Maria airport, but they do have a 24/7 weather signal going on. So it'd be kind of cool if we could pick that up.
Yeah. How much space do you have at your place in the backyard or whatever? Backyard?
Good. It's a good amount. Yeah.
Do you think?
I don't know the exact area, but it's, I mean, I could probably find out, but
Yeah, but if I gave you a spool of copper wire, you could run it around in your backyard and try and make it as long as possible.
yeah,
Yeah.
probably.
Probably get somewhere over 10 meters.
Oh, yeah, definitely. Yeah.
I think you could do it. Yeah, I think you could do it.
Yeah, I think I could probably get a